Hi, welcome to the video presentation of the final project being MIE1453 sensor level. We are Group 7 with the Aquarium, monitoring, and other system. So the idea of this project is to create a system to measure the CO2 and ammonia level in any home aquarium. To achieve that, we use the MIE1453 gas sensor for sensing the CO2 level and the system of LDR light sensor with ammonia pad to measure the ammonia level in water. The two sensors will be controlled by the Arduino Nano controller. So currently, the solution to measure CO2 and ammonia individually. The available is testing kit, CO2 drop checker, or ammonia alert pad, to name a few. However, the disadvantage of the current solution is that they are hard to use. They can be expensive when you buy them individually, and they require regular human input to be able to function properly. So we built a testing prototype with the aforementioned sensor to solve the inconvenience of the current solution. The new design can continuously measure the CO2 and ammonia level 24/7. The cost of the product will not be higher than the buy of the current solution. It's easy to use, easy to set up, and require no human interaction.
In this section, we are going to talk about the digital filters implemented in the prototype. Filters are needed to remove sensor noises for more reliable and a smoother reading to sense the physical phenomenon that we're interested in. We have implemented the two digital filters discussed in class, and the first one we're going to talk about is the simplified common filter for the gas MIE1453 sensor. Through our tests, we've discovered that it's quite a noisy sensor, but at the same time we need a quick response from it because our method of creating CO2 underwater is quite rapid, so we want to have something that responds quickly. There are two main parameters per se for the filter. One's the sensor variance and the other is the process variance. It's noticed as R and Q. For the sensor variance, we leave the gas sensor at a static condition, so in an ambient condition, and then we took the raw data reading, which is, as you can see in the red line in those graphs, and we've computed the variance of the signal recorded, which is approximately 2400 ppm squared. We use that value for the filter. And for process variance, we have to tune it manually, which is to we have to tune that manually. We've tried different numbers for it. We've tried it from 0.1 to 10, and in the end, we've decided to go with a Q value of 5 as a trade-off between the response time as well as the smoothness of the signal. As you can tell for Q equals 0.1, the top diagram there, signal is rather smooth, but the response time to that impulse, it's quite slow. So we decided to go with somewhere in between, that is somewhat smooth signal, but without sacrificing the response time. For the second sensor, which is the light dependent resistor, the LDR, because we know that the response time is a bit slow from the ammonia indicator pad, from the spec sheet, it takes approximately 10 to 15 minutes to change color, so we know that we have more time to go with a slower filter. Hence, a rolling average filter is used. We've also created our own circuit divider, voltage divider circuit, just because we ran out of the pin from the board, analog pin from the board, and we have to separate the LDR from the sensor board itself. We've chosen quite a large resistance so that we can maximize the voltage difference between the yellow reading and the blue reading, which also gives us a more stable sensor reading. And we take the average of 7 successive readings of the LDR. So here I'm going to show you the demonstration video of our prototype. The first one is to demonstrate our ability to detect ammonia in water. Here there is the reference for us to see. There's a identical pad inside the light shield, which is shown in black there. We have 0.1 milliliters of ammonia cleaner solution in the syringe, and on the top you can see the OLED display saying that ammonia and CO2 level are safe at the moment. So now we are injecting the ammonia solution into the water body. It takes a bit of mixing just to homogenize everything that's in the water to mimic excretions and water like other activities happening in the aquarium. So as expected, the ammonia pad does not change right away. It takes a bit of time for the indicator to sense the presence of the ammonia and change color from yellow to blue, which will then be picked up by the light-dependent resistor. So I think it takes about 30 seconds to a minute maybe, and then there you go. That's the alert, which is shown in the blinking LED. As you can see from the reference indicator pad, that it's turned blue. So the LDR is able to detect another pad which is inside the blue shield already, and tells the Arduino to sound the alarm. In the next video, continuation of it, we are going to show you the CO2 monitoring of the prototype. So as continuation of the past video, for the sake of the demonstration, we have removed the ammonia just so we can access the water. So right now, in order to sort of silence the alert, we have shunted the signal pin of the LDR with the ground. So in the OLED display, you can see that it's shown the ammonia level as undefined, which also quiets the alert. So right now, we're just gonna remove the light shield with the detector, with indicator pad in there. We will add a bit of vinegar, just so that it will react with the baking soda and then create CO2 underwater to mimic fish breathing in and out underwater. And I put the lid back on. So this is considered a safe level of CO2 just above the surface. And now we add in the baking soda. A small spoonful of it. Pour it into the water vinegar mixture. And now that the alarm is sound, the CO2 created from the water, it's bubbling or sort of vaporized into above the surface, and you can see that there's a huge increase in CO2 concentration just above the water level. So for further improvements for this prototype, we would like to do more testing at different conditions, different tank sizes. Hopefully we can also compensate for the CO2 reading, the sensor readings with temperature and humidity sensors. Better shielding for the light shielding for the LDR, so it's less affected by ambient light. Also tuning of the alarm threshold could be done more rigorously, just so we can determine when it's safe or when it's not safe for aquatic life to be in the aquarium. We can also have some phone applications for real-time monitoring and alert. And moreover, we can also have some sort of pattern recognition for preventative actions. For example, it can recommend you to feed less because there's a huge ammonia surge and persists over a long period of time. Or it can adapt its alarm threshold based on the time of the day. For example, if it's nighttime and there's less activity with the fish, or the plants are not conducting photosynthesis, the sensor can adapt to it and say, okay, we can accept a higher level of CO2 because it's nighttime, but we will sound the alarm if it is in the daytime and things are not right in the water. And that is the end of our presentation. Thank you very much.